In this video, we're going to connect those circuit elements together to make an entire circuit. Right now, all we know about the circuit elements are what their individual VI characteristics are, how the current and voltage are related to each other because of the element's construction. When you connect them together, we have to not only connect them physically, but we have to have the laws that govern the voltages and currents when elements are connected together. And these are called the Kirchhoff's laws. And there, as you might expect, there's a current law and a voltage law. And what we're going to find that once we have the VI relations, the KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law, we can solve any circuit. So let's start with a very simple circuit. And here we have three elements connected together. I have a voltage source and two resistors that are connected together one after another in what's called a series configuration. And what series means is that if I was an electron, this is the way I like to think about it, an electron, if I try to go out of one element and I have no choice but to go to the next one, that means they're in series. So we have an entire series configuration of a voltage source and two resistors. All right. Now, I would point out that we have three circuit elements, and we have a voltage and current for each element, which means we have 6 unknowns. And in order to find 6 unknowns, we're going to need 6 equations. All we have right now are the VI relations. So I'm calling the voltage across R2 our output, just because I wanted to. And here's the VI relation for the source, and here it is for the two resistors. And of course everything could be a function of time, as I've indicated. Alright, but 3 equations isn't 6. We need 3 more, and that's where the interconnection laws come in. Alright, so the first one we're going to talk about is Kirchhoff's current law, KCL, which basically says the sum of currents entering a node or leaving a node equals 0. So what's a node? So we look back at our circuit. A node is a connection point. That's where 2 or more elements are connected together and they're really attached. So in this circuit, I see a node there, I see a node here where R1 and R2 are connected, and I see a big node here where essentially R2 is connected to the other end of the voltage source. And this wire going between them, as we know, is just a short circuit, an ideal wire, and it doesn't contribute much to anything. There's no voltage drop, and the current just goes through it as it would normally. So I'm going to consider this one big node. So we have 3 nodes. And what I'm going to do is I'm going to write KCL for each node, and I'm going to do it in terms of currents entering the node. So let's consider them one at a time. So for the blue node, the current entering from the south, the current going in that way, is minus I, and the current entering from the east is minus I1. Right? You just flip the sign to reverse the direction of the current arrows. And so in terms of currents entering a node, minus I minus I1 is 0. Okay? We go on to the next node, and the red node, the current entering from the west is I1. The current entering from the south is minus I out, so I1 minus I out is 0. And then finally for the green node, currents entering, we have I entering here and I out entering there. So those, we have 3 nodes, we have 3 KCL equations. Well, I want you to notice something about these KCL equations. If I were to add these 2 equations together, and take a minus sign and negate it, I would get the other equation. And that's not good. Remember, we're trying to find 6 equations and 6 unknowns. And if the equations are not what's called linearly independent, they don't do as much good. There's, in some sense, one too many equations here. So what's going on? And what's going on is a detail about KCL and the construction of every circuit. So if you think about this circuit in 2 pieces, so we have the big yellowish kind of area here, and then our green node at the bottom. Because KCL is satisfied at each of the individual nodes here, the sum of currents leaving the yellow surface has to be is I plus I out. Well, those currents have to leave and go into the green node by definition, so that gives us the other KCL equation of currents entering. So it turns out that in any circuit, if you have n nodes, you have n minus 1 KCL equations that are linearly independent. You only need to write it for any set of n minus 1 nodes. You can pick anything you want. As you're going to see as we go through the course, we typically write circuits such that there's always sort of a node at the bottom where lots of things are connected together, and that tends to be the one we don't write KCL for. And so I'm going to throw out that equation. I don't need it. It can be derived from the other 2. So let's move on. We're going to need another equation. We've got 3 VI relations, 2 KCL equations that are independent of each other. We need that last equation so we can solve our circuit. And of course that's going to come from the voltage law. So Kirchhoff's voltage law is that the sum of voltages around any closed loop in a circuit must add up to 0. So here's our circuit, and we have 3 voltages here that are defined, and what we're going to do is go around a little loop. And the way you do that is, if we define we're going around the loop clockwise, that's what the graphic says, we're going to take the voltage signs according if it goes plus to minus. So I'm going to bring in V1 with a plus sign, V out with a plus sign. But over here, V is defined minus to plus, so I have to bring it in with a minus sign. And that's my KVL equation. So from one point of view, I'm very happy in terms of solving my circuit. I've got 3 VI relations, 2 KCL equations, and 1 KVL equations. That's 6 equations. We should be able to solve our circuit. But a similar issue arises with KVL that does in KCL. How many KVL equations are there actually for any circuit? Here there's only 1 loop, but how about this circuit? How many loops are there? Well, I get 1 loop involving the voltage source R1 and R2, and I get another loop out here in, that's surrounded by R2 and R3. However, I'd point out there's another loop, and that is the green loop. That's also there too. Well, it turns out the number of KVL equations you need is determined by how many open areas there are in the circuit. If you thought about this as a window, and these were pieces of wood holding together the pieces of glass, the number of KVL equations is the number of pieces of glass. In this case, 2. So the number of KVL equations I would write would be 2, and I'd write it for each pane of glass, if you will. So that's how you find the number of KVL equations that you need to solve for any circuit. All right, so let's solve that circuit. So we have 3 VI relations, we have 2 KCL equations, and we have 1 KVL equation. Aren't we happy? All we're interested in is finding what the output voltage is for the given source voltage. And we have 6 equations and 6 unknowns to plow through. So we want to eliminate everything. We will eliminate all the currents. We want to eliminate V1, and we want a just relationship between V and V. And with a little bit of going through this and thinking about it, it's actually pretty easy to do, and I won't go through all of that agony. I'll just say that after some manipulation, you should be a little worried about that. It's easily shown that what you get for an output is that it is the output voltage is proportional to the input voltage, and the constant of proportionality is given by the ratio of R2 to the sum R1 plus R2. It turns out we have derived this in general, right? We don't have specific resistor values, we've derived this in general. So anytime you see a voltage source attached to two resistors in series like this, you'll always find that the voltage across a resistor obeys this rule. And in fact, I'm going to ask you to tell me what is the voltage V1. And I want you to do that without doing any calculations. I want you should be able to just tell me what that answer is. All right, well, that relationship that for voltage across a series connection of resistors is called voltage divider. And the resistors split the voltage. Divided is where the terminology comes from. So the bigger R2 is, the closer the ratio here is to 1. The smaller R2 is relative to R1, the smaller this proportionality constant gets. So what does our circuit do? So remember, what we're trying to do is build systems, and we're trying to build them at this point out of circuits. So in terms of block diagram models, we have a source that's producing some voltage Vn, and there's the source is literally the voltage source in this circuit. The system is the entire circuit it's attached to, and we have taken as an output the voltage across R2. And what our system, the input-output relationship we have shown is given by that expression. So what does our system do? Have we encountered a system like that already? And the answer is we certainly have. It serves as a kind of amplifier. The gain of our amplifier is simply R2 divided by R1 plus R2. And because our gain has to be less than 1, resistors are always positive valued, it turns out we have an attenuator. And so what our little system, our circuit does in terms of system theory is that it serves as an attenuator. It makes voltages smaller. So let's do a little power calculation. I'm very interested in what is consuming power and what is the source of the power that's being consumed. So, as we know, power for each element is the voltage that we have times its current. And I want to consider that for each element. So, we know for a resistor that the power is the voltage squared divided by the resistance. That's V times I for a resistor. And since we solve for the output voltage, we might as well use this version of the formula. So what we get is that the voltage output, the output voltage, just to remind you, was R2 over R1 plus R2 times Vn. So you square that and divide by R2, you get that. And similarly, the power dissipated across resistor 1 is given by a similar expression where R2 is replaced by R1. I think that's pretty easy to see. Because these are positive valued powers, right? Resistors are always positive value, and we're squaring the voltage coming in. It turns out that means these two resistors dissipate power. They consume it. Well, it has to come from somewhere. So let's see what's going on with the source. Now, the output current is what we need. We need to find We have the voltage V, that's just given by the source, and we need to find the current I that's going in. Well, for a series combination, I think it's pretty clear that I1 equals I out, and that I is equal to minus I1. So, if I just find I out, which is given by the voltage that we found divided by R2, we know that that is I out, and I will be equal to minus I out, and what we get for a power produced by the source is the negative of Vn squared divided by R1 plus R2. And negative means it produces power. It is the one that is producing the power in the circuit. You add these two up, you add everything up, you get 0. And that's the way it should be. It has to be that power is conserved. There are going to be parts of a circuit that consume power, and there's going to be parts that produce it, and they have to be in balance, or there's something wrong with the calculations. And so no net power is produced or consumed by a simple circuit. And that's the way the laws of physics are. So, and this is the general formula that if you, for a given circuit, if you sum over all the circuit elements, the sum of the VK, IKs have to be 0. We'll prove that later. So, along with the VI relations, KVL and KCL always give you exactly the number of equations you need to solve any circuit. So you have to go through them all. And of course you don't need all the set of equations. What I mean by that, if they're an n-node circuit, you need n-1 KCL equations. And for a number of openings in a circuit, are only the number of loops you need for which you write KVL. Now, I do not want to spend my life solving lots and lots of sets of equations just to find an input-output relationship. So we really need methods to streamline our calculations, and we're going to talk about those soon. And it turns out they're very easy to use, and not only simplify our life, but give us insight into how circuits behave. Now, a little bit later, I'm going to prove that only KVL and KCL are needed to show that every circuit conserves power. The sum of the VK, IKs is indeed 0. That's really interesting, and we'll see that in a succeeding video.